Good afternoon and welcome everyone to the most recent webinar in the 2DCC series. Today we have Dr. Joan Redwing, who is the director of the 2DCC, and she's also professor of material science and engineering here at Penn State. She'll be talking a little bit about where we're at in the 2DCC after year 5 and where we're going. Joan Redwing, please go ahead.
Okay, thank you very much, Kevin. So for those of you who don't know, Kevin serves as the operations manager for the 2DCC facility here, and he keeps us on track. So what I'm going to do today is to tell you about the status of the 2D Crystal Consortium Materials Innovation Platform Facility. And what I thought I'd do is to start out by giving you a short overview of the facilities that we have and also the activities that have been going on over the past 5 years. And then I want to tell you more about the new equipment that we have coming in and the new initiatives that we have planned moving forward over the next 5 years. Okay, so the 2DCC is a national user facility funded by the National Science Foundation, and it's focused on advancing the synthesis of ultra-thin two-dimensional materials. So we were initially funded by NSF in 2016 for 5 years, and we just were recently renewed for another 5 years. And the funding that we received from NSF has enabled us to establish state-of-the-art facilities for 2D material synthesis that I'll tell you a little bit more about. We've also been able to develop advanced computational approaches to accelerate scientific discovery in this area. And our facilities are used both by faculty, staff, and students here at Penn State, and who are part of our in-house research effort, as well as researchers outside of Penn State in academia and national labs and industry. And also we sponsor a variety of educational and training activities that are geared specifically towards students and early career researchers. So the 2DCC is continuing our primary focus on developing 2D layered chalcogenide crystals. And this class of materials has continued to grow in importance over the past 5 years, with the emphasis on topological quantum materials and 2D superconductors and magnets, and also photonics and optoelectronics based on layered chalcogenides. And these are some examples of user publications in those topical areas. And 2DCC continues to be focused on advancing the synthesis of this class of materials to enable wafer scale processes and discovery of new materials and phases, and also to establish material metrics to assess quality. So now I want to quickly step you through the user facilities that we put in place at the 2DCC. And these facilities are located in 2 nearby buildings here on campus: the Millennium Science Complex, which also houses the NanoFab and the Materials Characterization Lab, and also the Davy Lab facility. So this first facility is the Thin Films and Insitu Characterization Facility, and it's directed by Nitin Samarth and myself, with contributions from Roman Engelherbert as well. And we have state-of-the-art equipment for epitaxial growth of 2D chalcogenides by metal organic chemical vapor deposition and molecular beam epitaxy. And the unique feature of our thin films facility is the integration of characterization equipment within the deposition tools so that we can measure properties such as the surface electronic structure using ARPES or the Raman spectrum without exposing the samples to air, which is particularly important for these ultra-thin 2D materials that are air sensitive. We can also monitor their growth in real time, and we can transfer samples between the tools using a vacuum suitcase. And this is part of our highly integrated vacuum environment, or HIVE for short. And we recently upgraded the ARPES to add a multi-wavelength laser source, the first of its kind, and this enables measurements with significantly higher energy and spatial resolution. And these capabilities have enabled us to develop sophisticated epilayer structures. So for example, to study emergent phenomena, such as the quantum anomalous Hall insulator state. We also study fundamentals of van der Waals epitaxy to improve the crystal perfection of the layers. And we're developing in situ diagnostics, which are of growing importance as the field of 2D materials moves towards technology and commercialization. So our bulk growth facility, which started basically from scratch in 2016, really took off once Professor Zicheng Mao joined the 2DCC in 2018. And it now includes a very comprehensive suite of equipment for bridgman and vapor transport and float zone growth of chalcogenide bulk crystals, and all of the associated equipment that's needed for sample prep. And these capabilities have enabled us to develop new quantum materials, such as the intrinsic magnetic topological insulators that were developed via in-house research efforts and are now drawing considerable interest from users. We also have expertise in bulk growth of ternary chalcogenide alloys, and that's enabled us to greatly expand our materials portfolio. And also the synthesis of chalcogenides such as niobium triselenide, which crystallizes in a one-dimensional structure rather than 2D. So in addition to our experimental facility, we also have a theory, simulation, and data facility. And this includes Vin Crespi's group that specializes in first principles calculations of the physical and electronic structure and properties of 2D van der Waals crystals. Also, Audrey Van Duin's group. So Audrey developed the reactive ReXFF force field technique, and that can be used along with molecular dynamics to study and model kinetic processes, and that's needed to describe synthesis techniques such as MBE and MOCVD. We've also been able to add capabilities in computational fluid dynamics simulations, and that's enabling some new efforts in multi-scale modeling. And finally, during our first year of operation, we recognized the need for a facility-wide system to capture and organize the large amounts of data that we were generating. And so we initiated the development of a web-based data management system called the Lifetime Sample Tracking Database, or LIST for short. And I'll tell you a little bit about that later on. Okay, so just some information on our user program. So our user program is engaging a very diverse and growing external user base. So far we've sponsored over 149 user projects, and those projects are led by 82 different academic groups with significant representation from non-R1 institutions and minority serving institutions and primarily undergraduate institutions. We've also had 9 national labs be users of our facility as well. And we have 3 industry user groups as well. And we sponsor different types of projects. So for example, this is a plot of the projects broken out by project type as a function of time. So one of the projects that we sponsor is a sample request, and that's designated in blue in this graph. So these are requests for materials produced by standard processes that we've previously developed. We also have research projects designated in red here. So these are typically aimed at developing new materials, or perhaps an external user wants to come on site and receive training and also use the equipment. Or perhaps they want to interact with our theory and simulation facility. So over the past 2 years, we also initiated 2 new types of user projects. The data request. So this is a project where a user can request access to information that's in our LIST database. And we've also started a visiting scholar program called RSVP. And that's targeted at bringing graduate students and postdocs and early career researchers on site to our facility for extended training and hands-on use of the equipment. And the pie chart that I have I'm showing here, this is a representation of the career stage of our users. So you can see there's significant representation from early career researchers, so graduate students and postdoctoral scholars and assistant professors. So the facility has been particularly beneficial to people who are starting out their careers in the 2D field. Okay, so all of the equipment and activities that we've put in place have fostered the growth of the platform over the past 5 years. And this is a snapshot of our accomplishments. So as I mentioned, we have a very thriving user program that's sponsored 149 projects so far, providing hands-on training to a number of users, and also a large number of high-quality samples that we've provided to researchers outside of Penn State. And then through our efforts on data management, we now have our LIST database, and that includes information on over 5,000 bulk and thin film samples that have been produced in the 2DCC facility. And as I mentioned, this has attracted a new type of user, external researchers who are interested in accessing the data for data science projects. Our theory facility also receives requests for ReaxFF parameters that have been developed for various 2D material systems, and we provide those outside of the user program. We have a range of knowledge transfer activities, including these webinars, as well as our annual Graphene and Beyond workshop, and they've impacted a broad range of researchers, even outside of our user base. And we've really worked hard to try to attract a diverse group of users, as I mentioned, including faculty and students from non-R1 institutions and MSIs and PUIs. And we engage with them to enable successful outcomes in publications and also in student training. And then finally, we've initiated partnerships with industry, including equipment vendors and small companies. And we have a robust usage by researchers at national labs. Okay, so publications are an important measure of impact and success. And so this is a plot of the 2DCC publications versus time as of the end of June 2021. And I've broken it out in terms of publications from our in-house research efforts, external users, and internal users. And I've overlaid the important milestones from the user facility development to give you a sense of how that correlates with publications. And you can see that the number of external user publications increased significantly starting in early 2019, after the 2DCC equipment came online and some of the initial user projects reached completion. And if we break it out by quarter, you can see that there's an increasing fraction of publications from external users. And the percentage of the 2DCC publications from external users has been continually increasing each year. And currently it represents about 40% of the publications over the last year and a half. A substantial number of publications are in high impact journals, including 18 in science or nature group journals, and 5 are listed as highly cited in Web of Science. Approximately a quarter of our publications include contributions from the theory and simulation facility, as well as our external facilities. And finally, over 90% of the publications are related to 2D layered chalcogenides, which just demonstrates the tight scientific focus of our MIP platform. Okay, so over the next 5 years, we're going to be putting in place several new pieces of equipment to enhance and expand the 2DCC capabilities. And so I just want to quickly step through some of these new initiatives. So this first item is a high pressure thermal evaporator system for the synthesis of 2D metals via confinement heteroepitaxy, or CHET for short. And Josh Robinson is the lead on this particular initiative. So the CHET process involves the intercalation of metals into the van der Waals gap in epitaxial graphene that's formed on silicon carbide. And defects in the epitaxial graphene play a key role in the intercalation process. But the two processes are currently carried out in separate systems where defects are formed, and then a separate system is used for intercalation. And there's air exposure of the samples in between, which can cause some problems. So what we're planning is a new system that's going to have an integrated plasma source and a thermal evaporator, and that will enable both of those processes to be carried out sequentially in the same vacuum chamber. In the bulk crystal growth facility, Zicheng Mao is going to be adding a double crucible vertical Bridgman system. So the Bridgman technique is a process commonly used for bulk crystal growth of materials that melt congruently. So that's the case where the melt and the solid composition are the same as you go through the phase transformation. However, many materials of interest melt incongruently. And that means that the melt composition is going to change over time as the crystallization occurs. And that can cause problems in obtaining homogeneous crystals. So to get around that problem, this system is going to have a second crucible that can continuously supply a source material into the growth crucible. And that enables active control of the melt composition. And this will provide a way to more precisely control the crystal stoichiometry, as well as producing much larger homogeneous crystals. In addition, this system is going to be capable of operating at pressures up to 10 atmospheres. And that's important for chalcogenides because you can have significant loss of the volatile chalcogen species from the melt at high temperature. So this particular technique was developed by Oxide Corporation. They're a company in Japan, and they developed this double crucible method for oxide crystals, such as the potassium tantalum niobate crystal that's shown here. So we're going to be working with Oxide Corporation, but now we want to develop this technique for chalcogenide crystals, and it's going to be the first of its kind in academia. So that will be a pretty unique system once it's in operation. Okay, one of the big advantages of the van der Waals crystals is that the layers are weakly bound to one another or to a substrate. And a lot of the very exciting science that's being done is carried out by exfoliating monolayers or few layers from bulk crystals, or transferring thin films from the growth substrate to another substrate. And this process, this ability to transfer layers and do stacking, has enabled the formation of heterostructures and also twisted bilayers, which have their own unique properties. And based on input from users, we're setting up a specialized Glovebox cluster tool for layer transfer and stacking. And this tool, which Joan in the physics department has designed, will have a computer-controlled transfer stage that can manipulate the layer position and also the layer orientation. And it will also have a built-in evaporator for the deposition of metals and oxides. And that's needed to exfoliate certain crystals that have stronger van der Waals bonds. Also, you can use the evaporation to passivate surfaces or to deposit electrodes using a shadow mask. And all of this, and also there's an atomic force microscope that's going to be integrated into the Glovebox for scanning probe characterization and to measure the thickness of layers, and specifically when you're making stacked heterostructures. So all of this equipment will be inside a Glovebox to prevent air exposure of the layers during processing. And the Glovebox is going to be incorporated into our Hive. That is the system where we can use the vacuum suitcase to transfer samples between the deposition tools. So now we'll also be able to transfer samples into the Glovebox for layer transfer and stacking. So this will be a nice system once it's online. So in the theory facility, we're going to be expanding our activities in the use of REACTS-FF reactive force fields to simulate the structure and chemistry of TMDs and other 2D materials. And as I mentioned previously, this work is led by Professor Audrey Van Duyn, and Audrey's group has developed force fields for most of the common TMDs, such as the tungsten and molybdenum sulfides and selenides. And they've been applying the force fields to simulate defects and grain boundaries in monolayers, and to also look at things like the crystal shape of TMD domains as a function of the growth conditions and the local chemical environment. And that's provided significant insights into the growth process. So as part of this expanded effort in the theory and simulation facility, users can request the development of new force fields for new 2D materials of interest, and also get access to the existing force fields, as well as theory and simulation support for their research. And then I previously mentioned our LIST database. So Conrad Hilsey has been the person here. He's our data specialist who developed LIST. And as I mentioned, it's used to capture all the information on samples that we produce in the facility. So this includes all the detailed recipes that are used for MOCVD growth and MBE growth, as well as all the characterization data. So all of the data, AFM, X-ray diffraction, TEM data, Raman photoluminescence data is all captured within the LIST database. And as I mentioned, we now have information on over 5,000 samples. So that's a lot of data, but it's really difficult to use it in a meaningful way just by intuition alone. So moving forward, we're going to be expanding the scope of LIST. We want to expand it from being a data archive to being a resource for discovery. And we've added Wes Reinhardt. So Wes is a new faculty member in material science. He has a background in data science, and he's recently joined the 2DCC team, in-house research team. So Wes is going to be developing data tools to use and build on the data that's now in LIST. So for example, he's interested in the creation of knowledge graphs. So these identify correlations between data, and they can be used to round out sparse data sets. They can also be used to predict outcomes based on the existing data. And this can be used for adaptive design of experiments and also accelerated process optimization, as well as the development of surrogate models that will help to better connect the theory and experiment. So we're very excited about our new initiatives in data science. And then in addition to the new equipment and technique development that I mentioned, we're also planning some new initiatives to expand and build the 2DCC ecosystem. So this includes expanding our visiting scholar program for graduate students and early career researchers, so we can provide more opportunities for extended visits at the 2DCC facility. We're also making the LIST database available to the broader community for data science research. And we have initiatives that are aimed at engaging government labs and industry and promoting collaborations between users through events such as our annual user committee meeting and also these monthly webinars that we host. And finally, we're building partnerships with other academic institutions and research organizations to collaborate on research aimed at applications of 2D materials. So for example, in quantum technologies and also in 3D integrated electronics. And I wanted to save some of this because in the October 2DCC webinar, we're going to have a speaker from our education and outreach team, and they're going to be providing more details on the plans that we have for getting undergraduates in the laboratory and also expanding our outreach activities. So with that, I would like to thank you for your attention, and I'm happy to answer any questions that you may have. And also, if you're interested in getting any more information, I just want to refer you to the 2DCC website. So thank you very much.
Okay, if anybody has questions, you may unmute yourself.
Professor, I'm Sai here. I have a quick question.
Oh, hi, Sai.
Yeah. So for the external users, right, if they want something like a sample or for any of the purposes that you mentioned, do they write a proposal, or is it more like, is it more descriptive, or how can you explain about that process?
Oh, yeah. So yeah, so both the sample requests and the research projects require submission of a short proposal. So typically, maybe one to 3 pages through our proposal submission portal. So in the case of sample proposals, it's typically just answering a couple of questions, describing the particular project that you have and what samples you're specifically interested in and how that will, impact outcomes. So yeah, the sample requests are handled the same way through the proposal submission portal.
Nice. Okay, so thank you.
Mm-hmm.
So Joan, I have a question about LIST 2.0.
Yep.
This is in, has it started already?
We're really just starting. Yeah. So Wes is hiring a postdoc, and I think the postdoc hasn't arrived yet, but as soon as that person arrives, then this activity is going to be ramping up.
Okay, so it will be we just need to send an email to if we have a specific.
Yeah. So are you interested specifically in like accessing data or?
Right. I want to find the one of those, for example, the Indian selenium sequence of material. See what.
Oh, yeah. So you could contact, I mean, probably your best bet is to contact Kevin at this point.
Okay.
Yeah, and just we can actually on the website you can go there and you can find out the different types of materials that are currently in list. You can get information on like the number of samples for a particular composition and material type. So yeah, we can show you where that is located on the website.
Okay. All right. Okay,
Yep.
Thanks.
Yeah, so I wanted to make a comment about the data request mechanism. So data request mechanism is very similar to the sample request. It's a one-page proposal. I recommend strongly that you contact us before you write such a proposal, because we can give you some insight onto data availability. So just because it says that list has 5,000 and some samples, remember that a lot of those samples are external user samples that are not yet made public. So the subset of samples that might be available in terms of data for a data request are different than what you see. What you see online is just a metadata explorer that will tell you what all is contained in list, not necessarily what is available through a data request.
Okay.
Professor, I have another quick question, if you don't mind. So I was also interested in that setup that you mentioned being developed by Professor Zunju for the transfer, right? The dry transfer within the Glovebox. Can you explain? Can you give an update, like how soon it will be, or like where will it be? Like I was also curious, where will it be?
Yeah, sure. So we have space over in Osmond Lab for that particular tool. Unfortunately, we can't fit it into the MSc building because there's just too much stuff here. But yeah, there's a room, the renovations are done. The transfer stage itself has actually arrived already, and they're starting to get that set up outside of the Glovebox cluster. I think the Glovebox is probably expected to arrive in another few months, but our plan is to have that available for users in early of 2022.
Okay, and that's a cantilever based transfer system under optical microscope, right?
Yep.
Okay.
Yeah.
Thank you. Yeah.